where we ended with Alex. So Simon is going to take it from here and talk about two of his projects and babies.
Okay. All right. So I will showcase a couple of tools that we've been working on in the past year and a half. And the emphasis of the first one, which is CBDA, compressive big data analytics, is on predictive analytics. So if you guys have data on which an outcome is already listed, binary, right now the tool works for binary outcomes, but we're working on expanding it on the multinomial, and it also works on continuous outcome. So if you have a data set that you want to classify and you want to extract some features, the most important features, feature mining from it, this is for you. So if you are on the SOCR news page and click on the link, the link is gonna lead you to GitHub, our repository, where pretty much everything is there. So it's open and you can access it and you can use it. We also have a CBDA R package. So I don't know how many of you uses R, but you know we developed the protocol, the methodology in R, and you know the package is available. If you click, so if you are on the GitHub and you click on the release, we got two releases. There was a beta release, and then there was the last one that has you know all the compressed file if you want to load the package. But most of all, it tells you pretty much everything on what to do to install it directly from CRAN, and some limits on memory and the overall methodology. We also have a paper that was that's published just less than a month ago. So all the technical stuff are in there. I'm gonna let me zoom in a little bit here. So this is the basic idea. So if you look at this flow chart, if you have a data set that is too big, the first thing that you want to try, and actually Alex was showing in the subsampling web app, so you don't want to process the old data. That was a simple clustering, right? But let's assume you want to do some classification with, you know, virtual machine, BART machine, generalized linear models. I mean, you need a lot of power. And so the first thing you want to do is to kind of break the problem in smaller problems. And that's the idea of compressive, kind of. And so the first step, which is represented in step 4 here, the first part is data wrangling that Alex mentioned a little bit. But the step 4, what it does, given some input, it's going to take pieces and parts of the big data and generate smaller data sets. And then plug this smaller data set into a black box that I will describe in a second. And it's going to do this thousands of times. Each time we're going to get an output, and the output is usually a prediction. That's the predictive analytic component. Now, each time we're going to predict something. At the end, we're going to try to reconstruct and combine together all this prediction into a single prediction. So there is a component that is based on subsampling, and there is another component later on that it's about putting together all the single prediction. And it's called ensemble predictor approach. Just I'm simplifying, but so there are 2 steps to the CBDA. One is to reduce the big data to smaller data sets, and the second component is to combine all the prediction all the parts into a better prediction. Here we describe several of these steps. The black box component in the CBDA is called the super learner. So many times when you have data, you really don't know what is the best algorithm to use to analyze the data, right? I mean, usually we use what we know better, and but we don't know if what we know best is going to work. With super learner, with particular black box in the which is the ensemble predictor component, we can, in principle, fill a big bag with all the algorithms that we want, machine learning algorithms. What the super learner does, it's going to combine all of them, and it's going to return a prediction that is as good as the best of each one of them. So what we're working on right now is to expand the library of algorithms that the CBDA uses to include as many as possible. And this will eliminate the burden for the user to decide a priori or set a priori the analysis on a specific algorithm, machine learning algorithm. The advantage of this approach is at the end of the process, the best prediction is generated, but it also is going to tell us what's the best algorithm to use for that particular data set. I don't know how many of you knows R or uses R. So yeah, most of the code is based on R, and the idea is that what's throughout the process, an object is generated that has information about two different steps. One is the training and the learning step, and the other one is the validation. I don't want to go too much detail of what's in the package, in the R package. If you scroll down, this probably So there's this example that eventually we can run together, so you can get an idea of how it works. The outcome of this process at the end is a list of the top features that are going to be most informative in generating the best prediction. So let's say I have a binary outcome. For example, in the paper we just published, we have the Alzheimer's disease data, and so it's going to be either normal patient or Alzheimer's patient. We don't know what features are most important to correctly classify the patient as either normal or, I think we have three actually categories in that particular data set. There will be normal, Alzheimer's disease patient, and there is a M is for mild cognitive impairment. Yeah, and it's kind of easy to classify between normal and Alzheimer's disease patient. But what's in between, the gray area in between, it's very hard to dissect. And the CBDA, we will reach, I think, a 96% accuracy in predicting those three different classes. On top of that, we can list the top features that will guide or they guided this fairly accurate classification. Right now, we're working on expanding the CBDA to deal with very, very large data sets. And I might just skip to the sifter now, or you won't? Yeah. So Again, later, I mean, if you have an issue of classification and big data, we can talk about using CBDA. The other project is completely different, and it's about so it's about sharing sensitive information, trying to preserve privacy, to limit disclosure, but at the same time preserve the utility embedded in the data. So disseminate data. In this case, it's EMR, electronic medical record. Disseminate data for scientific discovery. At the same time, try to preserve the privacy. We are almost done with publishing the first paper regarding this new technology. The idea is to start with the raw data that typically is requested from different entities. It could be research entities, but it could also be just private user or also commercial users. And this data, this request then are submitted to the data governor, which in this case could be the University of Michigan Hospital, and they need to be released in a way that whoever is using the data cannot dissect and sift out our identity. There are different steps that we allow in order to preserve privacy, and they're described over here. The most important thing is we combine, in general, we combine simple algorithmic procedures in a sequence, and we can control the amount of obfuscation we introduce in the data. So, for example, if the data governor, in this case the hospital, is confident about whoever's going to use the data, can just lower the knob and set the obfuscation to a low level, or we can increase it by increasing certain parameters. In this particular implementation, we call that knob the eta here, and it has several components. So the first component is about swapping certain features, that we call it unstructured features, between different cases. Then the other uses, the other two other component, they use the introduction of missingness and imputation techniques. The third component, the fourth component, the fifth component, they are related to swapping features among cases that are close to each other. And so we define different metrics to deal with structured features and continuous data, and also with categorical data. And we tested on synthetic data sets, but also on, I think we did some, we tested on the autism data. And we're working out now some theoretical results. The idea, though, is to show, for example, in this plot, and the x-axis is the eta that I was talking about. So that goes from 0 to 1. 0 will be absolutely no obfuscation. And on the y-axis here is the median, well, the match between the feature that we have in the initial data set and the resulting obfuscated data set. How many of those are matching? And you see, if we set the eta to 0, obviously all of the features are going to match because we are not obfuscating anything. If you go all the way to the maximum obfuscation 1, none of the features are going to match. So you see there is some sort of linear dependency between the eta and the amount of obfuscation. Now, this is an empirical test. So we're trying to work out the theoretical property. And out there's not that much that is 100% foolproof, in terms of preserving privacy. The top techniques are called differential privacy or fully homomorphic maps. And so right now we're trying to establish some relationship between what's out there and our method. Let me see. So this particular plot like this, they're trying basically to see how much of the data we can obfuscate. The other side of the story is, okay, but if we obfuscate everything, then there's nothing left in the data that we can use to gain any knowledge. So we try to balance this trade-off between preserving privacy, but also preserving knowledge. And the second part is a little bit harder because there's no a priori knowledge that we can target. So different theories, different researchers, they might have different questions to ask. And so depending on the question, depending on the type of model they want to apply, the obfuscation that we superimpose might have different effects on the knowledge that is obfuscated as well. Here there's an example of just a linear model. Oh, this is a logistic model applied to some synthetic data. But so we're trying to come up with some sort of generalizable metric to preserve that will give us some measure of how much of the knowledge is preserved in this obfuscation step. So this tool is if you have some sensitive data and if you need to disseminate this data and you want to try to preserve, you want to try not to disclose identities, information that are relevant. I guess that's it.
If you guys want to see, both of those can be demoed during the third part, so we'll just move forward so that we can have more. Thank you, Simone. All right, so let's see. Next would be Said, I guess. Right, Said with, okay, so he will plug in his own computer. Let me just one brief moment, say, just to stop sharing for a second. We'll put this over here. You need the VGA, digital. Yeah. You need a mouse or okay? No. Okay. I'm sorry?
I don't think I project.
Yeah, no, you are. This is your screen.
Yeah, this is the blue jeans.
This is still you. It's the same thing.
No, but that is this screen. That's not my.
The same thing.
No. This is this CPU screen. Just maximize the blue jeans.
Oh, I see what is. Okay.
Yeah.
But that's okay. It's full screen already. This is full screen.
No, like get rid of it.
Well, no, the sidebar you cannot.
Sorry about that. I'm Said. I'm one of the researchers working with Dr. Dinov. Most of my work, we do some machine learning-based classification of EKG systems. We do some visualization of neurological data sets, but the web app that I want to show off today is the SOCR dashboard. This is a tool for doing correlation and comparison studies on very largely heterogeneous data sets. We published a paper on this a couple years ago, and all of our code and work is also available on GitHub in case anyone's interested in contributing to it or keeping a copy of it for themselves. So over here, I have a almost clean version of the dashboard. All I did was I uploaded 2 data sets onto this. We have a Alzheimer's data set as well as a Parkinson's data set. So I'm going to start with, for example, the Alzheimer's. And this is, if you guys want to see, it's a very large data set. It's got a couple thousand entries with like 100 different features that we're choosing from. So I can choose any of these features and graph out a histogram or any other sort of chart for that sort of feature. And that's sort of like the basic visualization capabilities. But things get a lot more interesting if, for example, I also want to start choosing for the Parkinson's data set. Let's choose, for example, the left hippocampus curvedness. And that I can now, for example, filter or query the Alzheimer's data set, and that'll adjust the Parkinson's data set as well. So we can start examining these relationships between different data sets without doing any sort of data merging or mashing or anything like that in the meantime, which can be a little time consuming and difficult. And so Alzheimer's and Parkinson's, both of these data sets are fairly similar. They have a lot of the same features and they're fairly similar. But if we start using something that's a lot more different, so for example, over here I have data set that is for obesity patients. It's kinesiology data for them, so it shows statistics for them. And if I start using that instead, generally it would be kind of difficult for, comparing, for example, all these brain features against, how many pounds, an obesity patient can. But in this case, even with such different data sets, we can still start querying these ones. So for example, their BMI. And again, start seeing changes in the histograms for each of these patients based on the results for all these other data sets as well. And because of the way that we do this, we're bootstrapping and we're sampling each of these data sets separately. It's impossible to query down individual patient data, so it preserves anonymity, even if you're working with very sensitive data sets like. We can choose from a variety of different types of charts based on what sort of data set you're looking at. So we automatically look at, for example, whether it's qualitative or quantitative, the distribution, and a couple other variables. And based on that, we'll automatically recommend which sort of chart types are suitable for you. So in this case, for example, if we want to do a slightly more complicated data set, like a bubble chart, we can put, for example, our obesity data set on the x-axis and our Alzheimer's data set on the y-axis, and also have some selectors for radius based on, for example, our Parkinson's data. And for color, we'll just go with again. And now we have a lot more of a complicated data set, which again, we can filter through and manipulate using just these basic tools. And again, all this stuff, it gets set up very easily and very quickly, and we can do for example, a pie chart and start seeing, for example, the difference between males and females and how their statistics differ. But it works very smoothly, and you're able to do these studies across all these various different data sets that can be very differently formatted and have these very incongruent data sets, and still be able to run these correlation these correlation studies. One, for example, anecdotal example that happened actually yesterday was I was down inspecting the research results of these MDP students, and we had these 3 teams come up and show their stuff. And one of them was this team which had worked for about a year looking at data sets between opioid users and census data and economic data and all this sort of stuff. They were trying to figure out how these econometrics stats affected opioid use throughout the U.S. And it took them about a year of learning R, data wrangling all these very large data sets and coming up with some sort of suitable conclusions. And one of the questions I asked them was, are there other software data sets that you think could have done this for you? And they answered no. And I said, well, after the thing was over, I said, well, I mean, I can show you this one web app that could have done it for you. And what it took them about a year to query out and demonstrate and everything, I was able to do in about 10 minutes, and it looked a lot nicer too, if you ask me. So this is a really good data set, especially for people who aren't very strong in statistics and data merging and data wrangling, to really get off the ground and up and running and start really arriving at conclusions without too much in-depth knowledge of, for example, how to program in MATLAB or R, and how to do these correlation and all this other sort of messy stuff. We've done studies, for example, with combining census data, Bureau of Labor Statistics, physician data to see how physician quality varies based on economic status or race or gender and these other variables. So it's very good for using these healthcare, sociological, econometric, and pretty much any other sort of these tabular data sets. It's not just restricted to, for example, very medical patient-based data. And like I said before, all of this entire project is available on our SOCR website, so you can go to the web app right now. It's under our list of web apps, pretty close to the top of the data dashboard. And the code itself is also on GitHub if you're curious. It's always under active development, so we're constantly adding new features. Currently, we're planning on adding even more chart types and improving the way we handle this data mashing to make it even better. And yeah, that's pretty much all.
So, I want to mention that there is a video online.
Yeah, and we also have tutorials and videos that go over how to use this data set. Where did we? This is on the wiki.
No, it's on the main dashboard side.
Yeah.
Yeah. Okay. So if you zoom in, yeah, these.
So we also do have wikis and sample use cases, for example, that go over a lot more complex.
Zoom in, you got to zoom in.
No, it's not updating on this.
Right, but
that go over much more complex use cases. For example, like over here where we're graphing, state usage. This was what I was talking about before. We're comparing census, Bureau of Labor Statistics, and physician data. So we have much more in-depth use cases and solutions where we kind of show the full power of this tool and doing these really complicated studies, especially when it concerns these very large multi-source data sets. Yeah.
all right, sounds good. Thank you. So we're going to switch back to our screen sharing here. Okay, so all right, next would be Jerome. Before Jerome starts, I just want to point out here in slightly higher resolution what Said just mentioned a second ago. Right up here, you guys. Here are the links to the source code, the publication, as well as the video and the tutorial. If you want to look at some of these things, there is a protocol, step-by-step, well, video first of the video script, and then right up here there is a step-by-step, do these, download the data, screenshots of how to go about seeing some of these interactive charts, including, so basically you navigate and everything kind of updates as you make selections in the collage of charts. So have a look. That's a pretty cool application. We can do demos later on. I just wanted to point out. All right, so Jerome is going to now talk about the specific nutrition and obesity, and we're going to take another short break. Yeah, so it should be on in the collaborative.
Yeah. Oh, okay.
Download it.
Hi, my name is Jerome. I'm a Master's of Statistics. Today I'm going to talk about our second report of Mothers, Babies, Obesity project. So for our first project, we studied the relationship between maternal preconception BMI versus baby growth and comorbidity versus baby growth. Today, in this consecutive report, we will show the result for one of previous research questions about maternal preconception BMI versus baby growth using the larger data set. So at the beginning in the data pre-processing, we calculated the baby growth, the weight gain from the birth to their until their second visit to the hospital. Yeah, we have 6 cohorts. For female, their mother could be normal, overweight, and obese. Also, for female babies, their mother has 3 cohorts, so we have 6 cohorts case. We could find many of missing values. Each cohort has more than 40% of missing values. So, but ignoring these values could be a very bad idea because we could lose a lot of information, and sometimes there might be important factors. So imputation is a good method to deal with this problem. We substituted missing data with the average of each feature. So you can see several plus here for each cohort. Blue lines here means the observed data, and the red lines here is the imputed data. So the gray area means the completed values. Imputation has been done to the all of 6 cohorts, and we could get the completed data after that. Now, let's see the descriptive statistics. So, in summary, for each cohort, we can see male babies grown up faster than the female babies. This is the table for female babies, and this is the table for male babies. And also, overweight moms' babies grown up faster than normal and obese moms babies. For 6 months, around 6 months after, before their second visit to the hospital. And we can also see the histogram here to see the distribution easily. These are for female babies, normal female baby, normal mother's female baby, overweight mom's female baby, obesity mom's female baby. And these histograms are for times. So most of their second visits were between 6 months to 7 months. Male babies histograms shows very similar things. We can also see the violin plots. This is for weight. Y-axis means the weight change until their second visit from the birth. And there are 3 mothers' BMI types. Also, inside each violin plot, there are box plots here. And the width for each violin plot means the frequencies. So it's easy to see the distribution as well. This is for time of female babies. And also male babies for weight change and the time. So we implemented 4 kind of models, 4 approaches. So the first one is simple regression for each cohort. So we made 6 simple linear models. These are for male babies. So as we can see the results for each cohort, it's hard to say there is a relationship between baby's growth from the birth to the second visit and the time when they visit for all cohorts or the same. All of their R-squares were very low, below 20%. So it's hard to say simple regression is a good model to predict for prediction. And we can see the prediction as well. So this prediction is based on the time of 6 months after babies are born, and prediction plots. In this prediction plots, we can find blue lines, 2 blue lines for upper bound and lower bound. So for female normal babies, normal moms, it predicts they can be grown up. Oh, I'm sorry. .1213 kilograms after they were born, and for overweight mom, 4.076 kilograms, and the obesity mom, 4.09 kilograms. So this prediction is slightly different from the real data set. So the real data set shows overweight mom baby grows the most fastest, but there's no big difference. For female babies, 4.451 kilograms, 4.382 kilograms, and 4.452 kilograms for each cohort. Now we can also see our second approach, multivariate linear regression model. So there are three types of multi-regression linear model. So the first one, we will see the correlation between baby's growth and mother's BMI for each gender of babies. And the second model, we will see maternal preconception BMI between, and so yeah, we will see the correlation between mother's baby's growth and mother's gender. And lastly, we will consider both the gender and maternal BMI together to find the relationship with baby's growth. So here, for the first one, by gender, we have 4 plots. The first plot is residual versus fitted. This shows non-constant variance, and we can call it heterogeneity. So, regression basically assumes the homodicity, but our model shows not like that. So they are very concentrated here, nearby fitted value between 4,000 to 4,500. And this red line is a smooth curve that passes through the actual residuals, and it is relatively flat here and lies close to the gray dashed line. This is the gray line when residuals are 0. And also we can find some outliers such as 42, 540, and 1538. So second plot is about QQ plot. We can check the normality by seeing this plot. We can see here it shapes, it indicates that it has skewed distribution, and I think it's like left skewed and a little short-tailed. And we can recall that one of the assumptions of least square regression is that the errors are normally distributed. So if the points are very close to the gray dashed line, we can say they are exactly normally distributed, but I don't think this model is not following the normal distribution. For the third plot, it's about root standardized residuals and scaled location. So it's identical to the first plot here. The square root of the standardized residuals, which are residuals rescaled so that they have a mean of 0 and variance of 1. We can note that all values are positive. It starts from 0 to 2.5. The red line here also shows the trend of this distribution, and it still shows very non-constant. The last plot shows the standardized residuals against leverage, and just please note that the standardized residuals are centered around 0 here, and they are symmetric as well. this is what we can expect for normal distribution. But however, they are also very concentrated on nearby standard residuals between -2 to 2 here. And also leverages are very concentrated in only 2 spots. So also this plot contours value of Cook's distance. Cook's distance is increased by leverage and by large residuals. So on this plot, we want to see the red smooth line stays to the horizontal gray line here. Yeah, so okay. Right. Okay.
Kind of summarize.
Okay. Okay. So we can see the summary of this model that R-square is only 14% here. So both BMI and BMI overweight are not so significant in terms of p-value here. And also ANOVA shows that we have strong evidence that the time matters, but while the BMI doesn't. So we can also see the multi-regression plot here. The same diagnosis been done for the second model here. So in 95% confidential interval prediction, we can see each result for each cohort. We can compare all of them together later. By BMI, we also modeled and diagonals the same plus here. Also, we predicted 95% confidence interval here. For the third model, we considered gender and BMI together. So we have 3 independent variables for this model. We also predicted for 6 cohorts in 95% confidence interval. Now we will see the third approach. It's called generalized linear model. We transferred one variable called just age, and we also have to do imputation because we are considering all variables, not only for weight change, and also we have to we just standardize the weight change to binary, and after that we could get 6 full data sets, and then we modeled. So we have several fixed effects and also random effects here. So it's kind of mixture model. but the random effects was really low. We can see the variance and standard deviation. All of them were quite small. Also, in fixed effects, baby weight GM, this stands for the weight when they were born, was significant, and also just age was a little critical here. And most of fixed effects doesn't have meaningful correlation except just age here. Also, we could get the 95% confidence interval. So this is the result for it. Lastly, we used another data set. So this is very simple method. We just calculated the mean and the standard deviation, and then we could get the confidence interval using the real data. So the time is around 6 months, and there was not so big difference between our predictions. So after finishing this report, we can think about modeling another models. So all these simple linear regression models seems have problem in the normality. So also multivariate model indicates sex was also very significant. For prediction in real data, males babies grow faster than females babies in around 6 months. And also, obese mothers have the fastest growing babies, while normal mothers have the slowest ones. So prediction in simple regression shows the same tendency. However, multivariate regression was a little different. So direct comparison using the real data shows 90% of confidential interval that overweight mothers' babies will grow the fastest. Later, we can think about using multivariate regression models and generalized mixture model using different number of variables. So we can find the best model later. So also we can think about using non-parametric models, because all of cohorts seems like they don't follow the normal distribution. Yeah, this is all.
We will take a short break now, but before we do, I just wanted to show you, to state the obvious here, I guess, that this is a typical example of how we do collaborative research. You know, we work very closely with the collaborators, and I want you to think about, Jerome was too moderate, I guess, to point out the importance of how he organized this really complex and long report into something that you can navigate fairly easily as you go down and look through the analysis. You have first level, second level. There is a lot of complexity that's kind of nicely packed into a report that's dynamic. So if you're the collaborator, you can actually go through this report, and it's all very nicely, tightly packed so that you can, kind of navigate. Does everybody see with me here the navigation of this resource? This is all done through the, you can actually get the source code right up here. If you're interested in, the source code is over here. We can do an example later on during the final session. So why don't we take a little 5-minute break to stretch our legs here, and then we're going to continue, and then I want everybody to start thinking about